Good afternoon, students. Now we are going to discussing Unit 7. Unit 7. Now we are going to discuss Unit 7. Formation of carbon-carbon double bond. Formation of carbon-carbon double bond. The formation of this carbon-carbon double bond mainly involving in the important general methods for the formation of the carbon-carbon double bonds are elimination reactions, Wittig reactions from sulfones by decarboxylation of beta lactones by partial reduction of triple bonds, fragmentation reactions by oxidative decarboxylation of carboxylic acids from 1,2-diols, from aryl sulfone hydrogens and reductive dimerization of carbonyl compounds from organosilanes. So first we are going to discussing elimination reaction. Elimination reactions. These elimination reactions are mainly we are going to E1, E2, E1, CB reactions are there. These reactions are involved in the formation of a double bond. Just one example I am taken. When reacting with the base involving loss of HX, then forms double bond like this. And another example, when it is reacting with sodium ethoxide in ethanol solvent, then we are getting two products. So the Sedgef and Hoffman products will be getting. So these elimination reactions are again, next one is syn elimination reaction. Syn elimination reaction. Now we are going to discussing syn elimination reaction. In syn elimination reaction, the two eliminating groups are same side takes place. During the syn eliminating reaction, we are applying some heating. Therefore, this reaction also occur pyrolytic elimination reactions. Pyrolytic elimination reactions. So that is Cope reaction, Cope elimination reaction, Cope reaction or Cope elimination reaction. Hydrogen, alkyl esters upon heating, elimination of acetic acid, then forms a double bond will be formation takes place. This is a Cope elimination reaction. Next, we are going to Chugava elimination reaction. Alkyl xanthate esters. Alkyl xanthate esters involved in the heating elimination of thioester thiacetic acid, thioacid, then gives alkene is the product will be formation takes place. Elimination in sulfoxides. Elimination in sulfoxides. Elimination sulfoxide. When sulfoxides having alpha hydrogens, when sulfoxides having uh, alpha beta hydrogens, when sulfoxides having beta hydrogens, these beta hydrogens involved in the elimination of sulfoxide, then produces alkene is the product will be formation takes place. When selenium, similarly selenium oxide containing beta hydrogen, this sulfoxides having beta hydrogen that involves in the elimination then forms alkene is the product. When selenium also, when selenium under oxidation with hydrogen peroxide in tetrahydrofuran, then produces selenium oxide, selenium oxide. This selenium oxide having alpha beta hydrogen. This beta hydrogen abstract by the proton and involves in the elimination of selenium oxide compound. Then the product is this product will be formation takes place. Next one is anti-elimination of anti-elimination of beta hydroxyselenoids. When this beta hydroxyselenoids, when beta hydroxyselenoids, alpha beta hydroxy, when beta hydroxyselenoids reacting with uh, benzene sulfonide chloride, tosyl chloride or tosyl chloride, paratoluene sulfonide chloride, benzene sulfonide chloride. The tosylation takes place on hydroxy group. That tosyloxy group is a very easy leaving group. Tosyloxy group is very easy leaving group. Tosyloxy group is very easy leaving group. Therefore, when selenium having lone pair of electron, this lone pair of electrons donate the tosyl attached carbon, then tosyl oxy elimination takes place, then forms a three-member ring with the selenium positive charge will be formation takes place. When this compound again it involves in the this tosyl oxy attack at selenium positive charge and this bond shifting takes place, then the product is the product formation takes place. Next one is Wittig reaction. Wittig reaction. So the Wittig reaction is phosphorus ylides. When phosphorus ylides, reaction with ylides reaction with carbonyl compounds, then gives alkenes are the products will be formation takes place. Alkenes are the product will be formation takes place. This is a phosphorus ylide. The example for next one, synthesis of this phosphorus ylide is, next one we are going to discussing synthesis of this phosphorus ylide. When this triphenyl phosphorus, a trialkyl phosphine, a triphenyl trialkene phosphine reacting with methyl iodide, then it is involved in the elimination of iodine group. When this compound reacting with base abstract the proton from here. The bond formation between positive and negative, therefore I am writing CH2. When this compound, when this CH2, when this phosphorus ylide, when this phosphorus ylide reacting with when this phosphorus ylide reacting with carbonyl compound, when reacting with carbonyl compound, then the product is oxaphosphonaate. Oxaphosphatine B formation. This oxaphosphatine involves in the formation of alkene is the product will be formation takes place. This is the Wittig reaction. Next one is from alkene from sulfines. Alkene from sulfones. Alkenes from sulfone. That is Ramberg-Buckland reaction. Ramberg-Buckland reaction. So when alpha halosulfones, when alpha halosulfones R1, R2, alpha halosulfones when alpha halosulfones reacting with base. Base abstract the proton from other alpha side, alpha hydrogen. This negative charge involves in the displacement of halide ion. Then this compound is episulfone. This episulfone involves in the elimination of sulfur dioxide, then gives R2 R1 C double bond C R3 R4 alkene will be formation takes place. When the sulfones example is another example involving the sulfones formation of alkene is Julia-Lithigo reaction. Julia-Lithigo reaction. Julia-Lithigo reaction. This Julia-Lithigo reaction when phenylalkyl sulfones, phenylalkyl sulfones reacting with aldehydes in presence of alkyl lithium, then sodium amalgam ethanol, then gives E alkenes are the major product will be given. E alkenes are the major product will be given. Mechanism for this reaction when phenylalkyne sulfones reacting with alkyl lithium. Alkyl lithium abstract the alpha position of hydrogen from alpha position of sulfur because this sulfur alpha position negative charge is stabilized by resonance. This negative charge compound reacting with our aldehyde then gives beta hydroxy sulfones will be formation takes place. Beta hydroxy sulfones will be formation takes place. Beta hydroxy sulfones will be formation takes place. This beta hydroxy sulfones when reacting with the same tosyl chloride followed by reacting with the sodium amalgam ethanol, then elimination of this beta hydroxy and sulfones then forms one trans alkene will be formation takes place. Trans alkene will be formation takes place or E alkene will be formation takes place. Bis decarboxylation. Bis decarboxylation. So elimination of two carboxylic acid at a time at 1, 2 adjacent 1, 2 adjacent position or 1, 2 position. 1,2 dicarboxylic acid. Cis 1, 2 dicarboxylic acids when reacting with palladium tetraestate then gives elimination of 2 moles of carbon dioxide at a time. This is called bis decarboxylation. Then gives alkene is the product. Another example is The mechanism for this reaction is when reacting with lead acetate, then cyclic ester will be formation takes place. This cyclic ester involves in the elimination of two carbon dioxides at a time, then gives our alkene product will be formation takes place. Next, synthesis of alkenes from 1, 2 diols. Synthesis of alkenes from 1, 2 diols. That is, when cis are seen 1, 2 diols, when cis are seen, 2 diols, when reacting with thiopauxine, it is involves in the elimination of HCl. 2 moles of HCl, then the product is then gives cyclic thiocarbamate. Cyclic thiocarbonate. This cyclic thiocarbonate, when reacting with 1,3-dimethyl 2-phenyl 1,3-diazophospholidine. The structure of that compound is the name of this compound is 1,3-dimethyl 1,2,1,2,3-dimethyl 2-phenyl 1,3,2-diazophospholidine. Then gives alkene is the product will be formation takes place. Alkene is the product will be formation takes place. Alkene is the product will be formation takes place. Well, next one is alkenes from aryl sulfonyl hydrogens. Alkenes aryl alkene from aryl sulfonyl hydrogen. So that is called Shapiro reaction. That is tosyl hydrogen. Tosyl hydrogen of carbonyl compounds. Tosyl hydrogen of carbonyl compounds having alpha hydrogen, at least one alpha hydrogen, reacting with excess of N-butyl lithium followed by hydrolysis, then gives trans alkenes are the E alkenes will be formation takes place. E alkenes will be formation takes place. This is the Shapiro reaction. Mechanism for this Shapiro reaction is when tosyl hydrogen of carbonyl compound having at least one alpha hydrogen react with excess of N-butyl lithium by subtract the proton from alpha position of tosyl hydrogen of carbonyl compound and nitrogen position. Then therefore so when this compound involves in the elimination of tosyl group, then now it is involves in the elimination of this is vinyl lithium intermediate formation takes place. This vinyl lithium is quenched with different electrophiles. I am taking water molecule. Let's place the electrophile here, water. If I am added any external electrophile, then electrophile E product, electrophile addition takes place. This is a Shapiro reaction. Next one is McMurray reductive dimerization of carbonyl compounds. Carbonyl compounds reductive dimerization of carbonyl compounds. When carbonyl compounds and 2 moles of carbonyl compounds in presence of titanium zero metal, then undergo a reductive coupling, then gives alkenes with the major product will be formation takes place. Mechanism for this reaction is so how to preparation of this titanium zero metal means when titanium trichloride or titanium tetrachloride reacting with potassium or sodium metal, then we are getting titanium zero metal. So titanium trichloride, tetrachloride reacting with sodium or potassium metal, then we are getting titanium zero metal. So this titanium zero metal, okay, when titanium is a titanium is a metal, it is releases electrons to the carbonyl group. When carbonyls reacting with titanium is a metal, it releases one electron to carbonyl oxygen. This set mechanism, single electron transfer mechanism. then radical anion will be formation takes place. Radical anion will be formation takes place. This radical anion involves in the reaction with titanium 0. It is these molecules are observed on titanium 0 titanium surface. This is a titanium surface, titanium positive surface here. Or here radical is there. The bond formation between these two radical takes place. Or 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 titanium positive metal. Here now it is involved in the bond cleavage, homological cleavage between carbon and oxygen bond, then gives or and titanium oxide product will be formation takes place. Product will be takes place. This is this reaction is called McMurray reaction. This reaction is called MC Murray or McMurray. MC Murray reaction or McMurray reaction. Next, we are going to discuss Unit 8. Next, we are going to discuss Unit 8. That is synthetic application of organoboranes. Synthetic application of organoboranes. Synthetic application of organoboranes. So hydroboration. First, we are going to discussing hydroboration. Hydroboration. Addition of bromine and hydrogen is called hydroboration. Addition of boron and hydrogen is called hydroboration. Hydroboration means addition of boron and hydrogen is called hydroboration. When the main source of this hydroboration is B2H6. B2H6 is the monomer of B. It's BH3. BH3 is the monomer of B2H6. When this alkane reacting with boranes, then hydroboration takes place. Addition of hydrogen and boron atoms takes place. It is a cis type, cis or syn type. Some important application of organoboranes. Some important organoboranes reagents. Some important organoboranes reagent. There is dismyl boranes. When dismyl boranes is the structure of this is the structure of dismyl boranes. Dismyl boranes. This is the structure of dismyl boranes and thiaxyl boranes. So this is a thiaxyl borane. The thiaxyl borane. Thiaxyl borane. When 1,2,3 dimethyl butene. 2,3 dimethyl butene. 2,3 dimethyl butene reacting with the borane, diborane, then gives thiaxyl boranes. And 9-BBN. 9 bbn. So this is the structure of 9 bbn. These are the dismyl borane, thiaxyl borane, and 9 bbn are the some of the important organoboranes reagent. Organoboranes reagent. We are going to explain the applications of these organoboranes reagents. Now we are going to explain the synthetic applications of some organoboranes reagent. First one is proteinalysis. First one is proteinalysis. When organoboranes reacting with acetic acid, organoboranes when reacting with acetic acid, that hydrogen and acetic acid involves in the elimination of hydrocarbons. Hydrocarbons. Alkyl group on hydroborane. Alkyl group on boranes reacting with acetic acid. This acetic proton and alkyl group on boranes involves in the formation of hydrocarbons. Hydrocarbons. This is one of the example for proteinalysis. Yes. And the preparation of oxygen containing functional groups. Next one is preparation of oxygen containing functional groups. That is oxidation of boranes to alcohols. Oxidation of boranes to alcohols that is involves in the so boranes, trialkyl borane reacting with hydrogen peroxide, trialkyl borane reacting with hydrogen peroxide. So when hydrogen peroxide reacting with base, then forms uh, HOO minus. This negative charge and peroxide ion attacking on boron atom of trialkyl boranes. Negative charge on peroxide ion attacking on electrophilic nature of Lewis acid nature of boron atom, then forms trialkyl uh, trialkyl peroxide trialkyl peroxide borate intermediate formation takes place. This trialkyl borate, then boronate will be formation takes place. This boronate under hydrolysis, then this boronate under reacting with another mole of peroxide ion, then this oxygen and alkyl group is substitution replaced by the OH group, and another mole of peroxide ion then gives trialkoxyborane will be formation takes place. This trialkoxyboranes, then hydrolysis then gives ethanol, or the product will be formation takes place. Ethanol the formation takes place. Next one is carbonylation. I'll explain with the mechanism carbonylation. Here carbonylation, formation of CC carbon-carbon bonds, formation of carbon-carbon bonds, formation of carbon-carbon, that is carbonylation. Carbonylation, that is carbonylation, that is formation of alcohols, aldehydes, and ketones. So when trialkyl borines reacting with carbon monoxide at 100 to 125 degrees Celsius, then forms O. When it is under hydrogen peroxide in sodium hydroxide, then gives trialkyl. Tertiary alcohol will be formation takes place. So tertiary alcohol will be formation takes place. So mechanism for this reaction is when trialkyl borane reacting with carbon monoxide, the negative charge on carbon donates the Lewis acid of boron atom, then forms carbon bond, carbon boron bond formation takes place. In this case, one of the boron atom, one of the alkyl group, it is I'm writing like this. Alkyl group on boron atom shifting to carbonyl group of carbon monoxide, then forms or C double bond O R will be formation takes place when this compound involves in the lone pair of electron oxygen atom attack at boron atom, then forms negative charge. Again alcohol coming to here and pi bond shifting to oxygen side, then R. When this compound under hydrolysis, when this compound reacting with when this compound reacting with water molecule, when this compound reacting with water molecule, then epoxide will be opening takes place. R. Now it is involves in the formation of ketone will be formation takes place. Ketone will be formation takes place. When this compound reacting with sodium hydroxide, hydrogen peroxide, sodium hydroxide, hydrogen peroxide, then the product is it is involves in the hydrolysis. Tertiary alcohol will be formation takes place. When this compound reacting with only base, then gives secondary alcohol is the product will be formation takes place. These are the carbonylation reactions. Next one is formation of when trialkyl boranes reacting with alpha dichloromethyl ether, dichloromethyl ether, lithium stabilized dichloromethyl ether. Here in this case, this negative charge part here, negative charge here, positive charge, attack at boron atom. Then the product is negative charge ClCl or methoxy. Now it is involves in the elimination of chlorine atom by the attacking of alkyl group. And this molecule involves in the again shifting of alkyl group, migration of methyl groups. Chlorine group. Again, it is involves in the migration of rearrangement of chlorine and alkyl groups. When it is under hydrolysis, oxidation, then gives tertiary alcohols are the products. Next one is reaction with alpha bromoester. Next reaction with alpha bromo ketone or ester. Alpha bromo ketone or ester. When this compound reacting with the base, tertiary butanol, when reacting with base abstract the proton from adjacent to the carbonyl carbon, here negative charge, Br. Now this moiety is reacting with trialkyl boranes. Then the product is when it is involves in the elimination of bromine atom, and bromine atom place is replaced by the alkyl group. In this compound under hydrolysis with the tertiary butanol, then gives ketone will formation takes place. Next one is reaction with the diazonium compounds. Reaction with the diazo compounds. When trialkyl borane reacting with the alpha diazoketone, alpha diazoketone. In this alpha diazoketone, this negative charge attack at boron, then forms we are writing this molecule like this for our conveniency. Then the product is under hydrolysis. The product will be formation takes place. Next formation of amino derivatives. Formation of amino derivatives. Formation of amino derivatives. It is primary amines from first one is primary amines, synthesis of primary amines, amine synthesis. When trialkyl boranes reacting with the sulfonic acid, then forms primary amines. Mechanism for this reaction: when trialkyl borane reacting with sulfonic acid, lone pair of electrons and nitrogen donated to the boron atom. And it is involved in the elimination of SO4H minus, then forms RBr NHR. Now it is under hydrolysis, then forms RNH2 is the primary amines will be formation takes place. Next one is synthesis of secondary amines. The synthesis of secondary amines when trialkyl boranes reacting with azides, alkyl azides, then forms secondary amines will be formation takes place. The mechanism for this formation of secondary amines when trialkyl boranes reacting with the alkyl azides, negative charge on nitrogen donated to boron atom. This carbon negative charge, this negative charge compound donate the rearrangement the alkyl group from boron atom to nitrogen atom by involving elimination of nitrogen gas. when it is in undergo hydrolysis, then gives secondary amines are the products. Secondary amines are the products will be formation takes place. This is the organoboranes reactions. Some of the applications of organoboranes. Thank you.